We're now ready to restart. Do you hear me? Thank you. So once routers have computed their shortest path, we have seen that they can have multiple shortest paths to the same destination. Like here at A, there are two paths to D, to next hop that are F or C here. Well, this is considered a good thing, so this is why OSPF supports it, as it allows to exploit the multiplicity of paths that exist in many networks. This is very different from what bridges do, where they exclude everything that is not on the spanning tree. Here, in contrast, we would like to use as much as possible. However, that may not be without problems. So what should router A do when it has several packets to send to destination D? What is your best guess? What would you think you would do? So the poll should be open and speak up. I close the poll. And the majority says A, which is probably what makes sense, with a small issue still. Yes, we want to send to different paths to exploit the capacity of the network as much as possible. But if you remember TCP, a lot of the traffic on the internet is TCP. If we use multiple paths, then we might create some reordering. And if you remember some of the heuristics that TCP is using to detect packet losses may fail if there is a reordering. So reordering might cause some problems with the with TCP itself. You could say, well, we should fix TCP and allow some reordering, which is true, exists. There are versions of TCP, and in the slides on TCP that we skipped, we discussed some of them. There are ways to allow some minimum reordering and not detect a loss when you see things that are out of order. But what is typically done most of the time is try to avoid per flow reordering. So per flow means inside the same TCP connection, you would like that the network keeps the order of packets. So this is a typical requirement that many operators will have on the network. So many routers, all the routers that I know of, all the big vendors, Cisco, Juniper, Huawei, they all preserve the order of packets per flow. How is that done? Well, it's very simple if you use hashing. If you have, say, two possible hops, then whenever you have a decision, you hash the flow identifier of the packet. So this is, for example, the source and destination pair, source IP address, destination IP address. Sometimes you can also incorporate in that the port numbers, if they are available. If things are encrypted, you might not see the ports, but if they are available, you might use them. So different routers will do different things. So you take an identifier of the flow, which as the minimum is the source and destination addresses, and you hash it. A hash is a function that produces something that appears to be random between 0 and 1. And then you can do the following. If the hash value is less than 0.5, you take the first decision. If it's larger or equal, you take the second decision here. So if the hash is a good hash function, the first will occur with a probability 50%. So you will actually choose the next hop with equal probability, but you will guarantee that the same value of m results always in the same decision. So yes, we will do random decision, but in a smart way, such that packets of the same flow will go exactly to the same next hop. A desirable property of a routing protocols is that it is able to manage topology changes. And changes topology occur when there are router failures or link failures. So in fact, this is the major design goal of a routing protocol compared to a static configuration. You want to be able to have routes that are updated automatically if the network changes. So this occurs, in fact, this comes almost for free with what we've done. Link or router failures are detected by the hello protocol. In fact, most routers will implement something faster than the hello protocol. The hello protocol tests that the OSPF process in the neighboring node is actually responding to your hello, which is like a ping. There is another protocol called BFD, bidirectional forwarding detection, that is implementing on links whenever two devices, routers or a server and a router, are connected by a link. They can implement this a special protocol that will send, for example, every 3 milliseconds will send a quick ping message, so a BFD ping that will be sent from Ethernet adapter to Ethernet adapter. If this fails after 3 instances, that means after 10 milliseconds, a loss will be detected and reported to the OSPF process. So typically, this is what will done. So after 10 milliseconds, if a link crashes, this will be detected. If the OSPF process hangs, the node is still working, but due to a bug or some race condition, the OSPF process is hanging, then it's the hello protocol that will detect this. So when this happens, the router decides that this link is down, that this adjacency is no longer valid, so its local adjacency information has changed, so we'll change an updated link state advertisement we'll send to everyone. This will be flooded over all the links that work, and whenever a router sees a change in its topology database, it will recompute, rerun Dijkstra. Let's see an example here. This is a small network with only 4 nodes, and this is what the state of the network was after things have converged. So after Dijkstra has been run and everything has stabilized. So we have a simple ring, and if we look at node A, for example, node A has a topology database, which is illustrated by this graph. Of course, it exists not in the form of a graph, but a textual representation, but here I show the same graph. So the same topology database is present in the 4 nodes, and every node has run Dijkstra and obtained this routing table. For example, A, in order to send a packet to D, it has 2 equal cost paths that go to the east or the south interface. Assume now at time t0, the link between A and B crashes. This is the most frequent cases. Link failures are very frequent in the internet. So if this happens, then A will detect the failure, perhaps with the BFD protocol, will update its topology database. So its topology database, its local information, will say the link from A to B does not work anymore. So it will send a new LSA to all the neighbors, that's only C. It will send this new LSA saying, I have a link, my adjacency database is now only A to C with a cost of 10. C will receive, this will be sent from A to C, and of course, all of this processing takes time. There's a time to detect, there's a time to, it's very short time, we're speaking of millisecond, but it's not instantaneous. While this is happening, of course, the other nodes still have the old information. So for example, if D has a packet to send to A, then if we look at the routing table of D, because the topology database as D is this ring, D had computed 2 equal cost paths to A. One of them goes via B. So if D has a packet to send to A, it will send it via B, and it will not work because B will send it to A over a link that is filled. So this packet will be dropped. Worse, if C has a packet to send to B, for example, it may decide one of the two paths may decide to send it to A because C still has the old information. But A now, if it has a packet to send to B, well, it will not know where to send it, so it will probably drop it. But if it has a packet to send to C, for example, it might send it back to this here. So the routing decisions are now incorrect. Some packets will drop, and that might be loops here. During all the transient period, loops may occur. For example, this is what will happen here. Then after this update is received by C will update its topology database, flood it to all the other neighbors, that is to D, and will recompute Dijkstra. So now C has lost a path to B and will send everything to the east interface only. So now there will not be the routing problems, at least on this part of the network, but the rest is still inconsistent. And then you can imagine what happens. D will also receive this information, forward it to B. Sooner or later, B will also detect the loss of the link. It's every 10 milliseconds, but this is not synchronous. So perhaps B has detected it 3 milliseconds after A. So this packet will, this link state update sent by B that is detecting the failure might occur after here. And this will not bring new information, but will be flooded by everybody, and everyone will have the consistent view of the topology and will compute updated routes here. So at the end, we see that the loss here automatically triggers recomputations. As some of you asked the question on the chat during the break, it's heavyweight computation. It's true that in order to detect the loss and recompute new routes, we flood the information of the loss and have everybody recompute Dijkstra. We will see that there are other ways that cost less, but they may have other problems. In a case like this, they may take much more time to detect, to correct the correct value, to compute the correct value without loops here. Here, we see that as soon as the new topology information is flooded, then everyone has synchronized and correct information and computes the correct route. So the only problem is during the transient phase. Now, because doing graph computations on graph with hundreds of thousands of nodes was very difficult in the 70s, when computers you had in the 70s, but now is done in a fraction of a millisecond. So on the processors that you have in routers. So this is why this method is now a good method given the technology that we have here. So quick wrap-up question. When a router crashes, how do all routers in an area detect the crash? Here I assumed a link was crashing, but what if it's a router? If router B, for example, would crash? So the question is open in Speak Up. I close the poll in a few seconds. And the majority says A, which is probably the good answer. Certainly, this is how the the neighboring routers will detect it, and then their normal job as a link state router is to flood to the remaining adjacent routers, so all other routers will be informed of this loss of the new routers. The hello protocol will not allow all routers to detect the crash. It's only the neighboring routers, and the same for the BFD here. The timeout of LSA might also, in some rare cases, but the timeout value is very large. But if an LSA is not refreshed by the router that has crashed, this is a symptom that there is a crash here. So if it's not refreshed, typically this will also be detected as a crash, but this is not expected in principle. Routing protocols are very important in the internet. Of course, if an attacker can gain access to the routing protocol, then they can create a lot of trouble in the network. Of course, it's not so easy to gain access to a routing protocol. You need to compromise a router, and routers are not hosts. In principle, on a router, you don't go on the web via a browser, so they're much less exposed to outside attacks, so they are much safer. However, what is easy to do is to wiretap on the links between routers. We have seen that it's very easy to buy, for example, a switch, so you can easily break an Ethernet link, make a switch in the middle or a packet splitter, and get all the information. So what you need is to be able to avoid those problems. So this is done by using essentially authentication. The current value of authentication is that is done in all versions of OSPF. And here is an explanation of how it works. So there are various types. OSPF is very complicated because it has evolved over 30 years. But today what is done is OSPF type 3 authentication, which simply consists in adding a sequence number. It's a crypto sequence number in the sense it's not a cryptographically computed sequence number. It's simply a sequence number that is used for the authentication, which is different from the sequence number that is used by OSPF when it does an LSA. When it sends a new LSA, it gives a new sequence number to this LSA so that routers know when they are flooding whether they're flooding the current or a previous version. Here, the sequence number is added to every packet that you send, including if you resend a packet because it was not ACKed. Remember that OSPF uses a stop-and-go protocol for reliable transfer of its packets. So if you resend an LSA or any kind of other OSPF packet because you detected that it was lost or you think it was lost, then you add a different sequence number. You increment the sequence number. This is to prevent replay attacks. Also, this sequence number is meant to be permanent, so it is a very large number, and it contains a boot count saved to disk. So whenever an OSPF process crashes, for example, it will not restart the sequence numbers from zero, because that could be used for an attacker to wait until the sequence number has reached the level at which it was before to be able to replay an old number. So this is an example that is very interesting and should be used in practically any protocol where we have permanent sequence numbers through this mechanism here. So the sequence number is added to any OSPF message, then it's sent in the clear together with a hash. So the digest here is using a secure hash. For example, this is today a secure hash where you hash the sequence number, the message itself, the IP source address, and of course a secret key. The secret key is a key that you must find a way to distribute to all routers that are on same link. Same link, meaning if there's a point-to-point link, there are two routers. If there is a LAN with 5 routers connected to the same LAN, the 5 routers in the LAN must have the same secret key. So when one router receives from a neighbor router an OSPF message, it will recompute the digest because the sequence number and the OSPF message and the source address are in the clear using the secret key. And if the digest corresponds to the digest that has been received in the message, then we think if SHA-256 is secure, which is true today, that it is impossible for somebody to have modified this number. So this message must come from my neighbor and has not been tampered with by an attacker who could still read the messages but not modify them. So OSPF relies on authentication only in this version. With OSPF version 3, very often we add also encryption, not just authentication, but also encryption. Encryption will make it impossible for attackers to even see what is visible, what is in the packets. And here the idea is that the less the attackers know, the more secure it is. So with encryption, with authentication, attackers are not able to modify the messages, but if the messages are visible, attackers will still gain information, for example, about the topology database that may be used for mounting other types of attacks. Somebody asked in the chat, how large can an OSPF network be for this to work? And that's an excellent question. Of course, because we flood all information to all routers, it doesn't scale to very large networks. So if you have a network, if you're a global operator and you have operation in all countries in the world, you may have a few thousands of routers, and you may not want to run this in all networks, in all routers. In particular, the flooding, which works well because we have processors that are powerful and the information we have is not large. Well, we're talking about textual representation. We're not flooding images or videos, but still, there is a limit to what can be done here. So if you have a very, very large network, typically huge providers that have presence in all countries in the world will use BGP. So they will treat their different countries as different networks, different domains, which often is the case, and they will very often treat them as different domains and use an inter-domain routing protocol that we will see in a few more weeks. But there is another technique that is used in OSPF, which is called multiple areas. So it's a hybrid between distance vector and link state routing. So it works as follows. If you are very large, typically you have also a well-organized network. You don't have a full mesh with arbitrary connection between routers if your router is very large, because nobody is able to manage such a huge thing. So if your network is very large, it's typically organized, and in practice, it is organized between local areas and a backbone area. So OSPF has this concept. If an OSPF network is very large, you can structure it into one special part of the network, which is called the backbone, and local, and the rest, which are local areas. And that typically corresponds also to the organization of your network. OSPF calls area 0 the backbone area. So it's a hierarchical organization with a very primitive hierarchy with only 2 levels. And then the principles are as follows. Inside every area, we use what we said before. We use link state. So there is one link state database per area replicated in all routers in the area. To make the link between areas, there are what is called border routers, like X3 and X5. X1 is not a border router, but X3 is. A border router is a router that makes the link between 2 areas, and it makes this link by being member of the 2 areas. This is in contrast to BGP. We'll see that in BGP, when you interconnect 2 domains, you must have a BGP router in each of the domains, which makes sense because BGP is typically for domains that don't belong to the same organization. But here, we are in one organization, so we can avoid having 2 routers and save some work and complexity. And then we make the link between the different areas by having area border routers, such as X3, inject into the areas that they belong to aggregated information. So X3 knows all the details of area 1, knows all the details of area 0, it will inject in area 0 not all details of area 1. If we would do that, we would be flooding all information everywhere, and that would be the same as having one single area. Instead, it will simply inform all other routers in the area of its distances that it has learned through area 0. So it is aggregated distance information. This is the principle of distance vector. Let us see on this example how it works. So here I'm zooming on area 2. In area 2, there are 4 routers. I'm showing also 2 stub networks, N1 and N2. And if I'm assuming this is all, of course, in reality, there's a huge number of prefixes, but I'm showing only 2. Every router in area 2 has this image, this link state database that I draw here. So all routers in area 2 will run Dijkstra, and they will compute their distance to N1 and N2. For example, X4 will compute a distance to N1, which is equal to 10. X4 will run the shortest path, and 9 plus 1 here, this is the shortest path. And also we'll know the next hop, which is B1, in order to go to N1. X6, in contrast, in order to go to N1, will have a different distance, and the next hop will be X4 here. So this is what we saw an hour ago. This is the link state principle inside area 2. And then, this is the trick here, X4 and X6 in area 0 will export this reachability information into the area as if N1 and N2 were directly attached. Remember, when B1 sees that it is connected to N1, it sees that through its local interface database, it will flood this information to everywhere. Here we will do the same. Not exactly the same, of course, we will give the information. It's not a direct attachment, but it's an indirect attachment. This is why we have different types of LSA. This is called a summary LSA, but mentally speaking, it's the same. So at the end of the flooding, all routers in area 0 will have this link state database. They will see that this router, which is X4, has a nose of N1 and N2 and a distance of 10 and 16. And similarly for X6, that has also a visibility of N1 and N2 and knows a distance to N1 and N2. And intellectually speaking, it's exactly the same as if they were directly attached with a cost of 16 and 10 for X6 here. Then all routers here will run Dijkstra. So router X3, for example, will run Dijkstra algorithm to know the distance to X4. And then if you remember, after Dijkstra, we said once we have computed all the distance to Dijkstra, we compute the distance to the stub networks. Here it's a bit different because N1 is not a stub network, because in fact N1 is attached to X4 and to X6 here. It's like a dual home network here, which is not a stub network. But it doesn't matter, the same can be done. Now, X3 views that N1 is attached to 2 routers, X4 and X6, so it will compute the cost of going and the distance and the shortest path if I choose X4 or if I choose X6. So I choose, will take all border area routers that are connected to N1 and N2, and I will compute the shortest here. So this is what X3 will do. For N1, it will compare what it costs of going via X4 versus X6, and that will give me a cost of 23. And of course, we compute not just what is the shortest, but we'll remember which of the one gave the shortest, and here is the first one. So X3 will see my next hop to N1 is via X4. So X4 is not a next hop, but I know how to go to X4, so I will compute what is the next hop to X4, which is X1 in this case. So this is how router X3 will do for all the networks that are visible through summary link state advertisement here. So at this step in area 0, all routers in area 0 know how to go to N1 and N2 and have a distance. Then X3 and X5 will do the same now in area 1. in area 1, X3 and X5 have computed those two distances. So the same will occur again in area 1. Now, all routers in area 1 will run Dijkstra with this addition and then use this additional information using this formula, which I call the Bellman-Ford formula. And A1 will find that its distance to N1 is 33 and that the path goes via X3, for example. So it will now know how to go via N1. So this is how OSPF mitigates the problems that we have if the domain becomes too large and we want to avoid flooding. So we have not flooded the topology. Here you see that the areas are isolated. Area 1 does not know of the topology in area 2. It knows only of the reachability information of area 2. Knowing only the reachability, that's distance vector. This is a vector of distances, right? We pass this vector of distances that we put into the topology database. So that's the principle. Quick question. When we apply the Bellman-Ford formula, how does A1 know? So this Bellman-Ford formula says, in order to compute a best route, I need to aggregate two things, the distance from self to a border router, and the distance from the border router to the prefix. By which mechanism did I get those two pieces of information? Okay, I'm trying to add a poll. Here I am. So you should see the poll now on Speak Up. I close in 5 seconds. And the correct answer is A. So the distance from self to the border router will be obtained from its routing table. This is the result of the Dijkstra computation. And the distance from the border router to N1, which is external information, comes from the link state database. It was flooded by the border routers. I skip the next poll, and let's discuss a few other things. Of course, you could say, why do we do link state if we can do differently? Well, the reason is that there are many constraints on this way of passing the information. In particular, the principle of distance vector, we will see when we study distance vector routing, has many problems if there are many loops in the topology. So the topology at the level of area does not have loop. The topology at the level of area is a tree. There is a backbone area, and all the non-backbone areas are connected to it. So we have a simple topology, and the principle of distance vector works well. It works well as long as the topology works. So one of the key issues in OSPF is what happens if an area is broken. For example, if the backbone area is broken, then we've lost what I said about the topology, or if an area itself is broken, then there are optimizations that make OSPF a bit complicated. The code of OSPF is very large to go around all those problems. For example, if there is a partition of a non-backbone area, then we can do, for example, if for some reason here the links, those vertical links would be broken, some of the links would be, those vertical links would be broken, X4, X6, and B1, B2 are broken, then the principle I showed will not work because the area is partitioned, we cannot flood inside the area, so the complete mechanism breaks. but there's a path here. We can go this way. So OSPF will find a way to make a virtual link between X4 and X6, and we'll expose it to the topology database to make this area no longer partitioned. So there are mechanisms like this, which makes OSPF very complicated. But if we accept that we work on having the topology of the areas as it is a very efficient mechanism to compute the routes and while being scalable. So we've seen OSPF, at least the theory part of it. I encourage you to do the quiz after this lecture. That will be posted shortly after the lecture. Of course, in the lab, you will discover some of the details. But I think it's important to know that the link principle of link state routing is used in many different settings. We use it for shortest path computation, and as someone asked in the chat, it's a bit disproportionate to have the entire view of the network and the only thing you do is compute the next hop. And it's true, and therefore OSPF is used for other things. It's used, for example, for multi-class routing. Since you know the complete area, you can compute different routes. For example, if you have satellite links in a network, you might decide that for audio traffic, you don't use the satellite links. So you might compute different routes for different types of service. And that's very easy to do because now you have the topology database and you can decide, you can run different instances of Dijkstra with different criteria. Some industrial networks use what is called explicit routes. Explicit routes are the same as source routing. So with explicit routes, and we've seen source routing an hour ago, so the edge router, it's not the source here, but the edge router will compute the entire path. So if your device, your industrial device, your smart grid phasor monitoring unit, for example, is connected to an edge router, the edge router will compute the entire path. Why do we want to do that? It is because we want to associate resources to this path. We want to do guaranteed quality of service, for example, to make sure that critical messages are always received within 2 or 3 milliseconds. So if you do that type of computation, you need to pin the routes, make sure they don't get recomputed whenever something changes. So they will be recomputed by the edge routers. And of course, if there is any change in the topology, the edge router will compute new routes. Those are various things. Here's another, perhaps a more interesting thing that is used in very large networks, like the network of Wi-Fi stations of EPFL campus. When we will be able to return to campus, we'll be able to benefit of this huge Wi-Fi network. There's 1,000 or more Wi-Fi stations on the campus of EPFL, and it uses virtual LANs. Whenever you connect to one station, you get an IP address from the local area network, from the LAN that belongs to this station. And if you move in the network, you will remain on this LAN using the principle of virtual LAN. If you do that at EPFL, then you have a huge, or a large campus, you have a huge number of virtual LANs here. So one solution that is used by a large-scale network is to tunnel the LANs in IP, which seems a bit weird if you think about it, but that solves the problem of mobility. Tunneling the LAN in IP, that means I have, of course, the only way to manage a large network is to have routers, not bridges here. So we have a network with large routers. We run OSPF or something like OSPF in all those routers here. And whenever there is a virtual LAN 2 here packet that has to go to a virtual LAN 2 packet there, we will put this Ethernet packet into an IP packet. Destination R1, and then R1 will see, oh, that's an IP packet that contains a virtual LAN packet. So it will look at the virtual LAN header and we'll see this is virtual LAN 2. I need to pass it to my virtual LAN interface here. So this is the idea. Now, if the routers have a link state database, then we could perhaps be smarter. In particular, how can we automatically create those tunnels. I can always do that manually, but if we think of mobility at TPFL, of course, we don't want to have somebody behind the screen associating the virtual LANs with where people are. So how does R7 know that the red virtual LAN is here, which is something that may be true today and might not be true tomorrow because it depends on the mobility of people. So how could we use link state routing to do this automatically? Automatically means, if you remember, if the red virtual LAN is here, I need to have tunnels. Tunnels means router R1 needs to know that R7 and R5, and only R7 and R5, are members of the red virtual LAN. So I need to send any broadcast packets, and I need to build a spanning tree with R1, R5, and R7. How can I do that if I have link state routing? How would you imagine, if you work at Cisco, that you would design such a system? I close the poll now. And the vast majority of you uses the solution A, which is a good idea, probably. B would not help. B would not help because if R7 hears MAC source address and puts it in the link state database, we still don't have this information. Is not useful if we don't know where the virtual LAN is. So R1 will know how to route to all packets that are local here, but will not know that he needs to create a tunnel to R7. So one idea could be to put in fact, this picture that is here, you can put it in the link state database by saying which interface has someone who is in which virtual LAN here. This is in fact exactly what is done by some system that is called, for example, Trill. So all routers will have exactly this map, and then router 1 here will see, oh, I must support virtual LAN 1, so I have to build a spanning tree with R7 and R5. I can build a spanning tree in different ways, but one way is to simply build a shorter, to agree on a route. For example, I might be the route, and then I compute the shortest path between the route and the different other routers that need to support this red virtual LAN here. So here I'm showing two spanning trees, two tunnels, in fact. This would be multicast tunnels. This is where we can use IP multicast here. So whenever a packet needs to be broadcast on the blue virtual LAN spanning tree, it will be sent in an IP multicast packet that will reach R3 and R6 here. And this is very easy to do by all routers if they have the entire view of the entire network, which they will gain from the topology database here. So this is, as far as I know, what is or was until recently deployed at TPFL campus with another protocol. It's not OSPF, it's IS2IS. IS2IS is something similar to OSPF. It's a competitor to OSPF. In the lab, we have public domain software, we have free software for OSPF, so we describe OSPF. IS2IS is very similar, but as you can imagine, being similar doesn't mean it's the same, so all the terminology is different, but the principles are exactly the same. There are different ways of doing that. Shortest path bridging is also used. If you now if you exclude virtual LANs, if you just think of the bridging problem, now we've seen that bridges by default are transparent bridges and run the spanning tree protocol. And this was justified by the fact that they are low-end devices. Now, if you buy a high-end bridge, not the one you buy for 30 francs from Migros, but an enterprise bridge, then they will not do just the spanning tree protocol, but they will do, in fact, shortest path bridging. So they will do exactly like OSPF. They will have a topology database with all the MAC addresses that are visible everywhere, and that will give much more support. This is used, for example, in high-end bridge network, for example, in video studios, where for some reason they use MAC layer only. Then you can do explicit routes, and then you can allocate the bandwidth that is needed for the very high bandwidth that is needed for the paths that support the video. Voila, that's all for today. So I hope you enjoyed the lecture, and in a few more minutes the quiz will be available online, and in 2 weeks we will start a lab on OSPF. Bye-bye now.